Thanks, Ian. So maybe start with a bit of background. So if you lived in California last year and looked out your kind of back window, this could well be what you saw. Year of huge blazes all over California, the biggest of which caused $17 billion worth of damage. And actually the first year that people were really attributing this stuff to climate change. And that's not kind of scientists saying that, that was the executive team and insurance companies saying that. 2017 hadn't been that much hurricane activity for a few years, and then we kind of had this. August 25th, we had the hurricane that hit Houston, Hurricane Harvey, completely flooded it. Second biggest hurricane losses on record. And then going into September, we had Jose, Irma, 3 storms barreling across the Atlantic at the same time, aiming straight for Florida. And then back in 2011, where at $330 billion worth of damage, we had the most losses ever in a single year, with the big earthquakes in, first of all, New Zealand, and then in Japan with the Tohoku earthquake, which was actually the biggest earthquake, magnitude 9, ever recorded in Japan. And of course, the tsunami then caused this. The Fukushima nuclear reactor got hit by the tsunami and exploded, causing huge amounts of damage. And this is interesting from a modeling perspective for kind of 2 reasons. The first is it highlights the fact that with catastrophes, you often get these kind of compounding effects of the one thing that you kind of know about, the earthquake, cascading into something that you didn't predict at all, the nuclear reactor blowing up, making the disaster much, much worse. The other thing, and I've got this weird Japanese script on the left, is, you might think of why on earth would you build a nuclear reactor right in the middle of where a tsunami might hit? And they didn't plan it. Actually, the models at that time said this was a really safe bit of Japan to be building in. But there was some active research, partly from historical records like this, and partly from some geological sampling that we're doing, that said actually in the 9th century, in 869 AD, there was almost identical tsunami that had hit. And it just hadn't been sort of updated in the models that we used for the nuclear risk assessment. So there's some interesting kind of elements to the data sets. So kind of putting this together, pulled from this website that Swiss Re have that allow you to do a lot of data querying on this. This is what the last sort of 30, 40 years of disasters look like. And I think there's kind of 2 things to really note here. One is that losses and insured losses, so blue is the overall losses and then pink is the fraction that's insured, are pretty steadily increasing. And the 2 worst years in record have occurred within the last 10 years. And that's actually primarily due not to do things getting worse, but due to lots of people building very expensive properties in Florida and California and places where it's really expensive. I think the other thing to note is that there's still a considerable gap between what's insured and what the total losses is. Which is something that, there's a sort of resilience gap there. And the final thing is really, even when you have these sort of terrible years and there's very big record losses, insurance companies don't really go out of business. So the modeling is actually pretty good. We kind of understand the stuff fairly well. But before moving off this, just sort of calling out that, I'm going to talk a lot about losses and dollar amounts and things. There's obviously a huge loss of life component to this, that the models are also useful. But you get different signals, right? So 2010, there was a huge earthquake in Haiti. Hundreds of thousands of people lost their lives. Not so much economic damage, obviously, but everything we're going to talk about is very much applicable on the kind of disaster management side as well. Okay, so what we do is we have a completely open source framework. It's all on GitHub. That's available for anyone to use to do this kind of modeling. And as well as the software, we actually have a community of practitioners, of scientists, of users. We have a couple of conferences each year, really to kind of have thought leadership and figure out some of this stuff. And we are sort of funded, get a lot of insight from the insurance, reinsurance world, but these tools are more broadly applicable than that. Okay, so that's a bit of context. For the rest of the talk, I'm going to sort of focus on 4 things. I'm going to talk very briefly about insurance. It's not going to be a big insurance talk at all. I'm then going to get into what these models actually look like, because they're a bit different. There's some interesting aspects of the models themselves. And if I've got time, I'll actually show you how we're using Jupyter notebooks to try and kind of communicate some of this stuff and some of the uncertainties in the models. And then I'm definitely going to make time for the 4th point, which is some applications of machine learning that are sort of emerging around this space. And it's not something we do per se, but we're partnering with different organizations to kind of look at some of these applications. And I definitely want to kind of cover that off. Okay, so very quickly on insurance. So property insurance, it's not just houses. It's kind of anything that you can own, any sort of physical structures, so houses, office blocks, hospitals, different type of energy facilities, wind farms, anything that you can build and might get whacked by some kind of a disaster. Then obviously you want to insure this stuff, so you have a relationship with an insurer, sort of AXA, Zurich, Aviva of this world. But actually, what then happens is the risk kind of gets concentrated in the world of reinsurers, and that's essentially insurance companies who insure the insurers. And that's kind of, from our perspective, the interesting bit, because it's those guys that have really a percentage of kind of all of the, say, hurricane risk in the US, because they're taking little bits of all of these direct insurers. So that's both where the risk gets concentrated, but where you have a lot of scientists and experts, really thinking very deeply about how to understand and manage this stuff. And then finally, we are seeing this, some of this stuff starting to transfer into the capital markets. And the big idea there is that this stuff should really be completely decorrelated with any other types of risk. If there's a big hurricane, there's no reason that the stock market should go down at the same time. So in theory, this should potentially be quite a kind of cheap, efficient way of managing disasters. And of course, so what insurers generally use are actuarial models, right? They use them for pricing. They use them for figuring out how much money they need to keep in the bank to pay out claims. And generally, these things happen quite often, and they're not that big in terms of the total amounts lost. So things like fires, thefts, accidental damage at homes. So typically, these insurance companies have tons and tons of data. The last 5 years of theft is probably quite a good predictor of what's going to happen next year. So you can just build statistical models and everything works fine. Not so good for disaster models. These are quite rare, high severity events. We don't have that much data on them. So you usually have some claims data from the last 20 years or so. There's historical events, maybe 100 years worth of decent data. And you've got scientific and engineering studies and research that you can kind of fold together. And is historical claims a good indicator of future claims? Maybe. Climate change is kind of completely mixing it up on the kind of storm, hurricane side. And then there's things like cyber risks, so cyber catastrophes that the industry is getting increasingly interested in using these techniques to model. And they've never happened before, right? So it's a pretty open playing field. So how do you do this stuff? Well, you build structural models, you take what you do know, and you build simulations on top of it. So just to sort of reiterate the problems then with building catastrophe models. So they don't happen very often or may never have happened before. They have unexpected and severe consequences. We saw the Fukushima reactor blowing up with the tsunami, Hurricane Katrina with the levees breaking and flooding. It was a very kind of similar scenario, completely unexpected side effect. And the past is not necessarily a good guide to the future. Okay. So in terms of the things we actually build these models for, because a lot of this has been driven by, where the sort of economic investment is, we have a very rich model set for North America, for Europe, some for the Asia and Japan. So, all the major kind of natural perils, earthquake, cyclone, tornadoes, windstorm, hail, etc. Terrorism's a kind of interesting one because, on the one hand, putting a 1-ton bomb in the middle of Piccadilly Circus, you can build a physical model of that, right? What's more tricky is how do you assign a probability of that happening in a given year? And there are approaches to that where people use game theory to work out likelihoods of particular attack modes. They're not totally accepted. There's some controversy in that. The other thing that you'll notice, and this is one of the areas where Oasis comes in, is there's a big blank area over Africa. There's a big blank area over a lot of the developing world in Asia. And there isn't really the funding to build these super detailed commercial models, but there also often is expertise in local universities or within the governments there. So part of the benefit of having these open source tools is it allows you to quickly build something that at least is a sort of first pass at understanding and managing the risk that can then develop and become more sophisticated over time. Okay, so kind of digging in a little bit more then to what these models look like. So on the left-hand side, we start with the event set. And this is really where the science comes in. So for a windstorm model, typically you'd run a sort of global circulation model on a big supercomputer. You get a few weeks on one of those. You generate millions and millions of years of possible events, and then you boil it down into something that was a bit more manageable and that you could actually run on a reasonable kind of business server. So maybe you'd end up with a few 100,000 kind of characteristic events. For each of those, you've then got a detailed hazard map. So you'd actually grid up whatever area you're looking at, and then have, for windstorm, say, it would be a sort of peak wind speed over some time period. For earthquake, it would be some measure of shaking. For flood, it would be a depth, a maximum depth of water. Coming down from the top then, you've got exposure data. So what are you actually modeling against? So the inventory of buildings, their characteristics, how much they're worth, where exactly are they? You have tools to refine that data, so geocoders to accurately place it. And then you stick this together to actually understand the likely damage. So the vulnerability is the other bit that goes into the model, and this is really the sort of engineering expertise. So, if I have a 2-story building, it's made of wood with a certain type of roof, and I blow a 90-mile-an-hour wind at it, what's the kind of probability distribution of its likely kind of failure modes? So you do that for all of the locations you're interested in, for all of the event sets. You have a financial model that implies the kind of insurance terms and conditions, and then you get some metrics out that you can make decisions with. and kind of digging into that a bit more. So the thing that comes out of these models that the insurance company or the kind of risk manager in a government really cares about is, up the y-axis, what level of loss am I going to experience, and the return period. So, 1 over the probability of it occurring in any given year. And it's actually sort of calling out a few interesting features of the data on the charts. On the left-hand side, you've got the kind of black square, and that's your actual experience. So as an insurance company, you've probably got 20 years of actual, real, detailed data that tells you stuff. The big blue box then is the 100-odd years of historical stuff, the storm record. So, you can use that in a kind of reasonable way. But then going out beyond 100 years, and this is actually, like if the regulation around an insurance company, it's actually the 1 and 200-year number that tells them how much they need to keep in the bank so that they don't go out of business. And we just don't have any data there. It's the opinion of the modeler. And we've got 3 models here for the same peril, and you often get wildly different opinions on this risk. So kind of digging a little bit more into kind of how these are put together. So the hazard model, the stochastic tracks, and the footprint that we saw on the last slide. You've got some historical data. You've got some scientific models. So for a windstorm, you actually have the fluid dynamics laws that you can use to sort of simulate this stuff. We've got the vulnerability data, which might be actual claims experience, what happened over the last 15, 20 years. You also have engineering studies, and there are labs where you build little houses and shake them a lot, or blow lots of wind at them and you just see what happens. So there is empirical data that you can use there. But the kind of interesting bit is what happens when you stick the 2 of those together. Is it at all feasible? And that's where the kind of expert judgment or secret sauce comes in, because the catastrophe models that pop out the end that people sell to insurance companies give credible losses, and people accept them, but there's this kind of black box calibration stage that there's not much kind of visibility into, which is a bit that the sort of users worry about quite a lot. Okay, so a little bit on the technology and how this stuff is actually kind of deployed. So this is what the insurance world has been doing for the last 20 years. So you've got your scientists, they use C++, Fortran, R, a bunch of tools to actually do the modeling. And they build the data sets, which then get, we're still in .NET or SQL Server world in terms of the applications. And then for the actual reporting, Excel, SQL Server, that's what these analysts like to use. And there, I've got a good bit of gorilla tape there showing how these things are stuck together. Actually, it's not a bad analogy because it's not pretty, but it works. This has been the sort of backbone of the insurance market for quite a long time. And if you want to unpick it and tidy it up, it's quite difficult and quite painful. So we're taking a slightly different tack and using all the kind of wonderful data science tools which now exist. And the key idea is that right at the heart of it, we have a Python package. So we actually have C++ components that do the sort of heavy lifting. So the millions of simulated events and location loss events that we need to do. And then we wrap that in a Python layer. And that's published on PyPy, so it's nice and easy to install. And that gives a kind of nice way of using the components either from the command line in a Linux environment or plugged into other Python tools, so that, as a model developer, maybe you don't actually need much else. You can just write Python code on top of that and all is good. On the enterprise side then, this stuff does need to be run at scale in a business. So Django, Celery, Docker, pretty standard toolkit, works very well. And then from the user perspective, we're on a bit of a mission to get the catastrophe modeling world onto Jupyter because it's just such a good fit. People are trying to understand and communicate complex models and reasoning with uncertainty in the loss distributions, and it's just painful with spreadsheets and usually ends up with copious amounts of documentation. So we're trying to, through examples and training, really push Jupyter in these applications. And then we're doing some pretty interesting work on how we actually really scale this stuff out. So some of the things we're looking at this year is deploying the models in a Kubernetes environment, how it integrates with things like Spark and big data platforms, or some of the cloud options. And we can't be too prescriptive with this because the organizations we work with usually have defined some kind of bigger strategy on how they want to run their big clusters of computers, and we want to fit catastrophe models into that rather than doing something different. Okay. How are we doing for time? Is that?
You're at 20 minutes.
Okay. So I'm going to skip over the Jupyter bit to make sure that I have time for the machine learning bits. So as I said, one of the, so we provide this open source software, but we also have a community of users. So one of the values of Oasis is that if there's interesting ideas that are applicable in the space, we can connect people up with the right people to actually use the stuff. And if appropriate, we also have these stuff, we have APIs, et cetera, deployed in these organizations. So it's a very easy way of getting new models or analytics being used in the insurance market. So to give a couple of examples around this, I've got 2 case studies who are with partners we're working with who are using machine learning. And the first of these is an organization called InsureData. And I mentioned it, the exposure data that you're feeding into the system is really critical. If you put rubbish in, no matter how good your actual risk model is, the results are going to be no use. So they've got, on the left-hand side, you've got a pretty sort of big error in the risk where you've geolocated it and it's just in the wrong place. So from a flood perspective, if it's 1.3 kilometers away, that could be on top of a hill versus right in the floodplain. So, huge disparity in the risk. So that's pretty crude. The middle one is a bit more subtle, where if you've got a house and you don't know much about it apart from it's made of wood, it's got 2 stories, you know where the lat long is. But actually just the fact that the entrance to the building, the main door is 3 or 4 feet off the ground as opposed to it surface level, again, could make actually quite a big difference to the risk. And similarly, if it was on sloping ground, so the entrance was 3 or 4 meters above the sort of centroid of the building, again, it could change the profile pretty significantly. And they've done a bunch of case studies. It's still a somewhat manual process at the minute, and they're sort of seeing this 20 to 100% impact. And that's, for an insurance company, that's huge. That's, they need to keep 20 to 100% more money in the bank to cover potential losses. So this is kind of what they're actually trying to automate. They want to, scrape pictures of buildings and then classify it. So they want to pick out features. They want to pick out where the door is. They want to try and measure, how high some of these features are and really check or validate the data that they have. And they're using neural networks and TensorFlow and Amazon SageMaker to try and automate some of these processes. And they say it's pretty hard. So the first is houses are pretty variable. Even the number of windows, the configuration of doors, windows, it's not like a face where you've got a nose, 2 eyes, and a mouth. in roughly the same place. So it makes the classification of that much more challenging. And then, of course, there's image quality. You know, you might have something that works well if it's a completely straight-on, well-lit image you're working with. But in the data they've got, there's often obstructions, lighting, the buildings are slightly offset, all of which really complicates the problem. So that's a bit of a work in progress. The next company is an Australian company, and they're actually using machine learning to kind of build models to replace some of the expert judgment that goes in. And as an example of that, I've picked out how they can sort of seasonally forecast hurricane activity. And their thinking was, so we've got this plot of sea surface temperatures. And climate scientists pick out features of these that they base a lot of their predictive power on. So a good example is the southern oscillation, which is the difference in sea surface temperature between Tahiti and somewhere in Australia, which will come back to me. And that's actually a really good predictor of El Nino, La Nina years, and hence things like hurricane activities that are related to that. And so they've sort of thought, well, hang on, we don't need to just restrict ourselves to these small set of kind of predictors. We can treat it like an image and use all of these sort of image processing and classification toolkits to come up with a whole bunch of different classifiers that might be useful. So they use unsupervised learning to create a bunch of these classifiers, which they correlate against kind of observed patterns, and then they actually use that to build sort of Bayesian predictors of what hurricane frequencies might be. So digging into that a bit more, this is what these guys produce sort of going into the hurricane season. So early June, they've got a kind of prior distribution of how many named storms, how many hurricanes, how many major hurricanes they think are going to come through. And this is a pretty competitive space, actually. There's a whole bunch of teams around the world who release these hurricane activity forecasts and really care about getting them accurate. And I think last year these guys actually came first, which is pretty cool to see these kind of algorithms actually working. So just to wrap up then, it's a pretty important discipline for kind of doing this resilience modeling, especially when things are moving with climate change and migrations of property and people. It is a quite established discipline. There's lots of techniques, there's lots of expertise, but loads of challenges and lots of potential applications of some of these sort of new data science techniques. And it's very ripe for innovation, and as a framework and a community, Oasis can really help get some of these new ideas kind of into the industry. I'll take some questions in a sec, but just to wrap up, we are looking for a Python developer. So if this kind of seems pretty exciting to anyone, sort of combining science stuff with Python development and working with some pretty smart people in the market, come and talk to me. And similarly, if this chimes with things you're potentially doing maybe in a completely different field, again, super interested in kind of figuring out some more collaborators in this space. So that's the end of the talk. Any questions? Yep.
With all the variables in the model equation, I mean, are there any tools to identify key variables that you could then begin to model better? I remember a technique of Jupyter method where you have a very complex system methodology to filter out what are the primary variables that we should perhaps be doing more experiments on.
I mean, it's not my total area of expertise, but I think that's kind of what the RIAS guys are doing. So there's obviously a huge scientific community who do a lot of research trying to figure out those variables, do the sort of scientific investigation. But there is potential for these more data-driven approaches that don't necessarily have the same sort of immediate physical basis to be very useful, increasing the kind of skill of these models.
Just a related question, is the industry using claim data to feed into the model so you can get better precision in calculating risks or the cost of damage?
Yeah, absolutely. I mean,
Can you repeat the question?
oh, sorry. The question was, are insurance companies using kind of their own data and their own claims data to feed into the models? And yeah, absolutely. I mean, if you're AXA, you know more about French windstorm damage than anyone else in the world. I mean, that's very valuable commercial information. So they have teams who are basically combining the data sets they have internally to sort of tweak the models. And from a technology perspective, that's, historically the models have actually been very hard to kind of play about with. So the sort of next generation is sort of opening up much more to allow people to kind of change any of the assumptions underlying them. So that's
Well, no, it helps. It's a shame that it's not shared.
the
The data, the claims, it's not anonymized, so you could actually feed it into.
yeah, but it's a kind of commercial advantage, I guess. Yep.
Just a quick one on my side. Really good talk, thank you. Question: what's the spatial resolution of Oasis, and does that change? And is it the same for your different parameters?
So we don't build models per se. So the spatial resolution could be anything really. You actually see a huge variability between something like a flood model, where it can actually make a huge difference, even sort of 10 meters away, because it could be in a gradient. The soil conditions could be extremely different. So you get high resolution flood models that in some cases go down to 2 or 3 meters. On the other hand, something like a wind model, there's no real point in doing that because, a windstorm is quite uniform over the scale of kilometers. So you have a much sort of coarser grid. The other thing that's quite sort of interesting from a modeling perspective is if you ask a sort of research scientist to sort of build the hazard fields, they're really interested in hazards, so they'll build you a kind of uniform grid and pick out all the features of it. But actually from a risk modeling perspective, you don't really care. You want lots and lots of data in the middle of cities or where there's lots of high value factories or whatever. And actually in the middle of desert or whatever, you need virtually no data. So you have sort of variable resolution grids that are optimized for risk as opposed to understanding the sort of hazard.
Thank you.
Should wrap this up. Yeah.
Sure.
Thanks.